we have been discussing magnetism, particularly magnetism of an ion or an atom with its electrons inside. And so, what one does is that one starts from the change in the Hamiltonian. See, the electrons are the ones which are responding to the magnetic field. So, one actually writes down the Hamiltonian for the electron in the atom or the ion. And what we found out is that there are three main terms in it. There is this term, first term, which is the straightforward paramagnetic term, this term, the first term. Then there is a, suppose this term vanishes, then we have to look for terms above it, beyond it, which is the second order term. Remember, the as we discussed, the susceptibility is a second derivative of the free energy. So, the second order contribution to energies you have to keep, and so if the first order contribution somehow vanishes, then of course, the second order becomes then important, and there is of course a third order term. So, these three terms basically come from for example, the first order term and the second order term both come from the spin of the electron and the orbital angular momentum of the electron that couples to the field, and the corresponding change in energy is given by the first two terms. So, the electronic configuration of the atom that we are discussing is extremely important, because all these terms L and S, their values are determined by the electronic configuration inside the atom or the ion. The other term, the last term, its source is slightly different in that it is coming, as you can see, from the size of the orbital is important. So, it actually comes from the rotation of the orbital, the alignment of the orbital plane of rotation shifts a bit when you put a magnetic field, and so that shift in energy comes from that. And so, this contribution is interesting, the last one, in the sense that this is, you will show, as we will show, this will give you a negative contribution to susceptibility. Now, if you remember your school days magnetism, then the susceptibility is chi is positive, then we call it paramagnet, and if chi is negative, we call it diamagnet. See, the diamagnetic materials, as we learned in the school, move away from the magnetic field and so on and so forth. So, that is basically reflected in the fact that the susceptibility is actually negative for so susceptibility is a response is negative. Now, as I said, these electrons are thought to electrons inside the atom, the ones which are contributing to magnetism. See, the closed shell, as we just show you, that does not contribute to magnetic in at least not the first term. So, and this is the major contribution. So, that we will we actually look for contributions from the electrons which are beyond the closed shell. So, for closed shell, of course, we will find that there is only term that will survive is this diamagnetic term, which I will just come to. The other thing I mentioned was that this term is the first term, which is the first order contribution to energy coming from the paramagnetism of the atoms is a much higher term compared to the diamagnetic term. The second term, of course, is also paramagnetic, but you see it has a denominator energy which is difference between two energy levels, and these are electronic energy levels which are typically electron volts. So, this is actually way down compared to the first term as well. So, once the first term survives, more or less magnetism of the material of the atoms of the concerned atom is determined by the first term. So, we estimated these to be at 10 to the power 4 Gauss. The first term gives 10 minus 4 electron volt, the last term gives about 10 minus 9 electron volt, and so on. So, that is the ballpark figure one is considering. And as I said, in a material, when you go to a solid or you are a collection of atoms, and remember here the atoms do not talk to each other, at least the spins do not talk to each other, the electrons do not talk to each other. Even inside the atom, the electrons do not talk to each other, because the inside is closed shell, and that does not contribute to magnetism, whereas the outermost orbital is the one which contributes. So, these are considered completely independent, and in such situation this is the Hamiltonian. If they talk to each other, of course, then we will have to add those terms, and they involve much more work. We will come to it at a later stage, particularly when the moments sitting at the atoms, at different atoms, talk to each other. Now, the typical, for example, this picture of susceptibility that you got in your school days, probably you have seen, or you may not have seen this, but this is what it is that you have paramagnetic susceptibility, this is chi, and this is temperature T. So, paramagnetic susceptibilities are somewhere here, diamagnetic susceptibilities are here, and free spin, these are called Pauli paramagnetism and Van Vleck paramagnetism, they are pretty close. So, Pauli, somewhere here is Van Vleck. These are terms I am using, I will explain what they are as we go on. We will discuss Pauli paramagnetism. So, and Van Vleck comes from a term, from the second term in this Hamiltonian. So, and then the free spin, free moments will give you free atomic moments will give you the free moments on the atoms are they have this much larger susceptibility and sort of diverges as T goes to a lower temperature. And the diamagnetic one is here, it is negative, this is 0. So, this is the typical graph that one sees in books and other places, and all of these are explainable in terms of quantum mechanical calculations as we are doing. See, this Hamiltonian, these have almost everything that you need to know for atomic magnetism. When, as I said, we go to long range ordered systems, atomic order, then one has to go beyond this. That is a very different approach, and that is where there you have to consider the moments on the atoms interacting with each other in different atoms. Okay. So, let us just go one more step. This is Larmor diamagnetism, this contribution from the last term, okay, is typically called the Larmor diamagnetism, and this corresponding susceptibility is the Larmor diamagnetic susceptibility. Now, this if you have a solid where the atoms are or ions have all their electronic shells filled, for example, in this noble this argon, neon, xenon, this kind of system, for example, they have completely filled shells, right. So, inert gases. So, they are of course, they are inert because they are completely filled shells. There you will have this this situation that L is 0, S is 0, therefore, J equal to L plus or minus S is 0. So, then so then everything, see, if since L is 0, L is 0, if J, and then J is 0, J is basically L plus S or L minus S, as we will come to Hund's rule. But then this is this the there is absolutely no moment sitting at the atoms. Electrons have no moment, total moment is 0. Now, so this is a situation where your first term vanishes, and remember the first term vanishes here. This term will also vanish, second term, because L and S are 0. So then one has only the last term to contend with. This last term is proportional to h square already. So, this will give me with a minus sign, and look at it, all terms here are positive, quadratic square terms, right. So, there is no way this term can give you a negative value, and then as we know that chi is minus 1 by V del to F. At a very low temperature, this F is basically E. So, so this will of necessity be 0 less than 0, and this has to be diamagnetic because of this minus sign sitting there, and this derivative being positive. So, the other interesting thing that you have to remember is that although I have written the energy for the nth, so whatever I have put here is n or n, so delta H n, n delta H n prime, this kind of things we have put in. Most of the times you will be dealing with n equal to 0, the ground state. So, the ground state is all that you are concerned with, simply because the magnetic energies, as we just found out, are so small that they are smaller than the temperature scale, typically they are smaller than any other electronic scale. So, you are more or less confined to the ground state, and so what one really does is to calculate the change in energy in the ground state, and in that case unless you are at finite temperature, where the finite temperature contributions add up to free spin moments, free moments, so that we will come to, but for most atomic calculations you are looking at the change in energy of the ground state. So, and so therefore, you are as is done here, the ground state, one has just taken the derivative here of the ground state, change in the ground state energy, and in the see, it says that if all but very high temperatures, there is negligible probability of the ion or atom being in any but its ground state in thermal equilibrium. So, your susceptibility is basically the two derivatives of the, instead of F we can safely put del to E 0 del H 2. Now, if we do that to this term, this delta E 0, as you can see, is E square by 8 m c square into 0 sum over I x I square plus y I square 0. Now, if you have a closed shell atom, then the atom is spherically symmetric, the electronic distribution is spherically symmetric, and then your 0 x I square 0 is the same as 0 y I square 0 equal to 0 z I square 0, and they, because they are three of them are same, so they should be equal to 1/3 0 r I square 0. Okay. So, if that is the case, then one can just replace this by 2/3 of r I square, and one gets delta E naught equal to E square by 8 m c square into 2/3 H square 0 R I square 0 sum over I. So, that is the result that okay. So, that is E square sorry E square by 12 m c square H square 0 sum over I R I square 0. Now, the sum over I R I square I can just replace by the average. So, if there by just the average R I for every atom, it has to be the same for every atom. So, I can just replace it by just R square for that atom times n. So, then what I get is susceptibility. Two derivatives will produce a 2 here is then going to be minus n by V del 2 E 0 del H 2 equal to minus E square by 6 m c square n by V 0 R I square 0 for n such atoms. So, that is the so this is the so all you have to do is to find out the Ri's of the ith electron in the atom and then sum over the squares and then typically one actually replaces this by the average size of the atom in and then you get a ballpark figure which is fairly correct. So, that is what this treatment does, and this is negative and you get a diamagnetic susceptibility. It is called the Larmor diamagnetic susceptibility. Okay. So, that is the theory of diamagnetism that comes out of these quantum mechanical calculations. Of course, as we are discussing, the need is to know these values of this J, L, S and so on. So, the next task is to find the values of L, J and S, L, S, J. These are quantities you need to find in an atom to do any calculation starting from this theory. So, that is the next stage and that requires something called Hund's rule. So, which you probably have heard in your atomic physics courses that how the electrons have to be distributed in a particular orbital. So, given an L value, suppose you are doing with d orbital is L equal to 2, then you will find out the corresponding this distribution of atoms in the system. So, for example, let us do the first understand what are these Hund's rules. So, they tell us basically how to fill up the shells in an electron. So, suppose you are given an L value, then there are these 2 into 2L plus 1, right. So, there are 2L plus, so given an L value leads to 2L plus 1 choices, right, from minus L to plus L, from plus L to minus L. So, and in each of them you can put a spin either up or down. So, there is this 2 into 2L plus 1 levels. So, the first rule says, this is the rules are written first, second and third. This order has to be maintained, because this is the first rule which is the most dominant rule. So, first rule is the most preeminent rule, then goes the second and then goes the third. You cannot first use the second rule and then the first, you have to first use the first rule. So, it is like the three laws of robotics in Asimov's books. You have to go by 1, which is the supreme, then 2, then 3 and so on. So, these n electrons are filled in 2 into 12 plus 1 levels, as I just showed. Then what you have to do is to first maximize S. What is the maximum value of S, which is basically the largest projection of S along the direction of quantization, which is the Sz, right. So, this Sz, maximum Sz is what you have to first put, sorry, maximum Sz is where the S can take the maximum value. So, largest value of Sz is the same as the maximum largest value of S. So, you put the electron in that. So, if n is less than or equal to 12 plus 1. So, let me just give you an example. For example, in this case, for example, this so L equal to 2 and you have 5 levels. So, then you have to maximize S. Suppose you have 2 L plus 1 electron, which means 5 electrons. So, you have to start from the lowest and then just put all the spins up. Why is this so? Well, a simple physical argument can tell you it has to be so, because of Pauli principle, because Pauli principle prohibits 2 electrons of the same spin from coming to from sitting in the same orbital, sharing the same state. So, then of course, you have to obey that, and that gives you a lower energy, and that is what this is done, as long as you can do it. But of course, if you have put 6 electrons, then you have to now put one of the orbit, one of these 5 you have to doubly occupy. So, that you have to do. So, up to 12 plus 1 S becomes its maximum. So, here for example, it is 5 by 2. So, so all 5 are up. So, this is this is the value of maximum value of S is each S is plus half for an electron. So, 5 of them. So, you will get this value. Okay. So, so after this you will have to reduce your maximum value by a half unit, remember. So, that is what it says, that S has to reduce by half. The next electron, if you have one more, you have to put it here. That means you reduce your total spin by half, because this one cancels this spin. So, instead of plus half, you now have 0 there. So, that is that cancels a half unit, and so on and so forth. You can keep on doing it. So, that is the first rule. Second rule is the total orbital angular momentum L of the lowest lying state has the largest value. This again is the same argument, that orbitals which are rotating in the same direction in a classical way of thinking are to be excluded from each other as much as possible. So, you do not occupy those orbitals first. So, you occupy one orbital, then look for another which is a different L, and keep on maximizing your L value. So, the first electron in the shell will go into the level with mod Lz equal to its maximum value L. Next we will go to L minus 1 and so on up to 2 L minus 1. So, the shell is less than half filled, then this is your L value. At precisely half filling, of course, L will become 0. So, I will work out one example and then it will become pretty clear. After half filling, go through the same series as the first one. So, then again you put 2 electrons and so on. The third one comes from a completely different argument. It is called the spin orbit coupling, which basically couples, particularly in higher atomic number atoms, there is a spin and orbit coupling that comes, and that is given by this kind of a term. Lambda is a constant and L dot S is the typical Hamiltonian or the typical energy for that for these orbitals, these high atomic number elements. And then then lambda also can have different values depending on the filling of the total number of electrons in that atom, in that particular shell. So, so this, since L dot S, L and S are now coupled, L dot S is the energy, L and S are no longer good quantum numbers separately. So, what is a good quantum number is the total angular momentum J. So, you have to go to the basis with J, and again there are 2 J plus 1 values, projections for J, from plus J to minus J, Jz takes these many values. Now, the lambda is negative. So, lambda is negative for lambda is negative for if the shell is less than half filled. So, and in that case J and then L and S are parallel. As you can see, L dot S is the energy, lambda being negative, they will try to align with each other. If lambda is greater than 0, which happens when n is greater than or equal to 2 L plus 1, then L and S are anti-parallel, which is again true if lambda is greater than 0, then this term will be negative if L and S are in opposite direction. So, that lowers the energy. And correspondingly, the J values are J equal to L minus S for up to half filling, and J equal to N plus L plus S for N greater than half filling. So, that is how you have to organize your atomic orbitals. The example is for example, d shell L equal to 2, which is a very important shell, which happens in the transition metal elements, that is the outermost shell in transition metal elements, 3D transition metal elements, 4D transition metal elements. These are the levels that get filled out. And so, from, for example, from scandium to zinc, these get in the 3D case, these levels get filled up, the 3D level gets filled up, and this is how you fill up. So, what you do is that you put, for example, you can choose to start with a down spin, up and down does not matter, you have to maximize S. So, which is the maximum value S z can take. So, that is the, so this you start filling up. If you have 1 electron, you put it in the largest L as the second rule tells us. So, first rule tells us this will be up. I mean, the first rule tells, here the first rule does not tell anything, you can put up or down, does not matter. Once you put it down, for example, if you have 2 electrons, the second one will go to down, and it will go, the first one will go to the largest L value, which is 2, and L z equal to 2, and then next one will go to the next L value, which is the next to the largest, which is L z equal to 1. So, and you see the third one will also have the same spin direction up to 5, which is 12 plus 1 here, you will continue to do it, right, and starting from the largest L z, so that your L values are maximized. So, that is exactly what one does. So, so your S keeps on increasing, at 5 you have 5 by 2 and your LZ now all the LZs are filled up from minus plus L equal plus L to minus L. So, your L is 0. Okay. So, that is how it is done. So, here we are not we will show you what J L dot S term does. So, up to this far we did not use the LS coupling or anything, but up to 5 by 2 we know the J value will have to be L minus S mod. So, to calculate the J value we have this L J equal to L minus S because you are less than half filled. So, beyond that you have to use J equal to L plus S and that determines the J value. Remember the term symbol, so called the term symbol, it is a historically designed one and these are basically the x 2s plus 1 x j. So, that is how you write the term symbol. So, 2s plus 1 is 2 here, j equal to 3 by 2 and the L equal to 2 is D level and so on. Okay. So, so this is how the scheme works for 3D or 4D levels, okay, or any D level L equal to 2 level. For F level it is you can accommodate 14 electrons. So, it is a bit more complicated, but you can go ahead and do it and as you can see that for F level which is L equal to 3 you can go ahead and do it. So, from minus 3 to plus 3. So, so 7 orbitals and this 7 into 2, that means 14 electrons have to be put in. Again you see that S is maximized up to this, then you have 8 electrons, now you have S reduces and then it continues this way and then corresponding J values are L minus S here and L plus S starting from here. So, that is the scheme of things by which J S L total S, total L and total J are determined, and these are the things that we need when we calculate those expectation values in the delta E sub n expression, right. And above so suppose n equal to ground state. So, we will find out the ground state electronic configuration and then put it on both sides and finally calculate those expectation values. Just one small thing, that is if this nth level is degenerate, then you have to diagonalize in that sector and that is how you do it in degenerate perturbation theory for example, and then use those levels. That is not difficult, it is not an additional big complication, but that is the way the scheme works and this is what we are going to do in our next class.